Welcome back. This is part 2 of the Dynare introduction tutorial. In this segment, we'll cover the shocks and computation sections of the model file. Just to review, on the right here we have our model file so far. It begins with the preamble, where we specify our variables, predetermined variables, exogenous variables, and parameters, as well as initializing our parameters. Then we have our model block, where we put down all of the equations of our model, and then our initial values and steady state block, where we specify initial values and tell Dynare to find a steady state for us. Remember that over here we have a stochastic version of this same model. All we've done there is moved our z variable into, changed it from an exogenous variable to an endogenous variable, and added epsilon as the exogenous stochastic process. We had to add a parameter rho that shows up in our law of motion for z. Alright, in this section we will talk about 3 different types of shocks and computations that we might want to do with our model. The first 2 will be for the deterministic case, and the third one will be for our stochastic case. In a deterministic model, we remember that everything is perfectly known. The agents, both households and firms, perfectly anticipate all shocks to the economy, and so we can observe anticipatory behavior and reactionary behavior as well, depending on how we specify our shocks. The first case that we'll look at is when we have temporary shocks. These would be shocks to our model that will occur for 1 or more periods and then go away, and the model, we can then observe how the model will move back to a steady state. To specify shocks in our model file, we begin with the shocks block. It won't surprise you that this begins by typing shocks and ending with a semicolon, and we'll end the block with an end command, again followed by a semicolon. To specify our shocks, we tell Dynare which variable we're going to be shocking. In this case, the variable is z. Note that these variables have to come from our list of exogenous variables. In this model we only have the one, but in other more complicated models you might have more, and you need to specify which one you're choosing. In any case, we have variable z. Remember that we have specified that we will be starting in a steady state here by using the steady command. So all of our simulations of this deterministic model will begin in the steady state. Consequently, we're going to shock the model in period 1, which is actually the second period of the model. The first period of the model is period 0. And just for fun, let's shock the model for 9 periods consecutively, and we'll set this aggregate productivity shock to 0.1 instead of its initial steady state at 0. So you can see that this is standard MATLAB notation for a vector, and that will specify that z will be 0 in the 0th period, and then it will be 0.1 for periods 1 through 9, and then 0 forever after. So this is a temporary shock. To do the computation with this temporary shock, we're going to we're going to simulate. To do this, and you'll notice at this point we're breaking from the pattern thus far of doing each block of the model in turn, and we'll cover shocks and computation together for each of these three cases. So to do this computation, the command will be simulate, or rather simu. The option, there's one required option for this command, and that is the periods command. Periods. And this is where we set how long our simulation is going to be. Now, because this is a deterministic case, everything will be perfectly known. So we're going to, likely what you'll want to do is increase the number of periods so large that there is no lingering effect of the shocks. If you set the number of periods too low, you'll see distinct last period behavior, because as everything's known, the agents know that it's the last period. So let's do 2000 periods here, and I'll show you exactly what I'm talking about with a shorter sample here in just a moment. Again, we end with a semicolon, and let's save that. Now let me show you how to run a Dynare model file out of MATLAB. Once you've installed Dynare, you should be able to just type Dynare and then the name of your model file. In this case, example. Now you can write .mod or not, either way will work. Note that your current folder has to be the folder that contains the model file. Let's press enter and see what happens in this case. Oh, it looks like I've made an error. The red errors out of MATLAB are going to be less helpful usually than the errors messages that Dynare itself will print. In this case, we have an unknown symbol A. You'll remember A is one of my parameters of my model, but my parameters I always list as C and then the name of the parameter. So I must have typed in A somewhere and then not used the CA that it needs to. To find that, we just look at what line this is on. It's in my mod file, obviously, and it's the first character of the 21st line. So let's go back over to my model file, and we go to line 21, and we notice that yes, I needed a C there. I think that should take care of the errors of this model file, and we'll try it again. Oh, I made another mistake. Once again, we have investment should have been INV instead of just I. So we can take care of this right here. One final mistake here is that I should have specified this with periods, not period. You'll notice that that's an easy thing to see, and it gives us the line that the error occurs in, and it says it's expecting periods or standard error. Obviously we wanted periods. I've shown you these three errors so that you can see how useful Dynare's error catching is. Sometimes it's quite difficult to track down the errors, but usually after a little practice with Dynare you can track down the errors you might have made in coding very quickly. So now we've corrected this error, saved our model file, and off we go. Alright, now let's examine the the output. These first lines of output just tell us which files Dynare is calling. That's not very important. It says that it's telling us that it's starting the pre-processing. It counts our equations. Remember that one of the very first things that Dynare does is check to make sure that the number of equations in our model block matches the number of endogenous variables, and in this case we didn't have an error. It computes our derivatives, and then gives us some results. So we finally get down to results here, and look here, we compute a steady state, and that's just what we'd expect it to be in this case. Note that it's not where we started, but it is certainly the closest steady state that it could find to our initial conditions. Now it simulates the model, and by iteration, by Newton's method, essentially, it is computing period to period what the model should go to. So that's the output. To see the real results of something like this deterministic simulation, we come over here to this variable OO underscore. This is a global variable that will have a lot of contain the majority of the results you'll be interested in, both in the deterministic and stochastic case. So let's open that up. Here we see that it has our exogenous simulation. It's just what we would expect. One variable, our z variable, for 2002 periods. It adds a period on the beginning and the end. And our endogenous simulation, the 7 endogenous variables over the same period. It also saves our steady state here. The rest of these are not very interesting for this particular simulation. Let's open up our exogenous simulation, and we'll go ahead and plot this shock. So this is our z shock. This actually isn't a very useful plot, but you can see that we get shocked to 0.1 for just the first short period, and then 0 thereafter. That's probably easier to see just here, that it's just what we told it to be. And you can see that here. In period 1, we jump to 0.1 and all the way up through period 9, and then 0 thereafter. Now, I misspoke earlier. Actually, the model will introduce 2 periods of zeros before the first period, so as to get because we have some forward-looking variables, it needs to give enough lead-in time for the agents to anticipate the first shock. So it added those 2 periods to the front end, not one on each end, as I said earlier. Let's look at some more interesting plots. Here we'll look at the endogenous variables. Now you'll note that there's 7 variables here. The order of the variables corresponds exactly to the order of our listing in the variable list in our preamble. So we'll have output, investment, capital, labor, interest rates, wage rate, and consumption. We can look at what that will, let's take capital for instance, and see what that simulation looks like. Now you'll notice that because we extended this period, the number of periods out to 2000, you have very little reaction at the end here. it will become very apparent what the difference is when I shorten the periods, the number of periods of our simulation here in a moment. But we have this response here in the front end, and then we move back to the steady state as we were hoping. To get a better look at this, let's just take the first 40 or 50 periods of our simulation and plot that, and you can see that with a shock to productivity, capital increases and then decreases. I think that's enough to illustrate what's going on with our temporary shocks to an indeterministic model. Briefly, let me just show you what I have been saying I would show you. If I decrease the number of periods to say 50, or even better, let's do 30. Save that and just run run Dynare again. You can see it's very fast in solving these. And here in this case, let's look at the same thing for capital. You'll see the behavior is markedly different because the agents are anticipating the end of the model occurring in period 32. So the behavior is very different. In some situations, this may be exactly what you're looking for out of your model. In some situations, not at all. So the useful trick is if this is not what you're looking for, if you're not interested in the end of simulation behavior, then just increase the number of the periods high enough where you don't get this reaction. Alright, let's now close out these and talk about the next type of shock. You know, before I do this, I should make one more comment about temporary shocks, and that is that we could have started the shocks later, say in period 5, if we wanted to study anticipatory effects more carefully. We'd also change our number of periods back to something long, and we can run that example and look at what happens to capital. In this case, we want to know just what the effects are in the lead up. You see we have a shock in the first 5 periods. Here we have excess spending in the first 5 periods because the agents are anticipating a productivity shock, an increase in productivity to occur in period 5. Alright, now we can move on to permanent shocks in the deterministic case. Again, note that these are going to be perfectly anticipated as it's a deterministic model, and we have rational expectations here. In the case of a permanent shock, we're going to delete our shocks block and instead use the end val command and have an end val block. Now the end val block is very similar to the init val block. In this case, we specify where we want our model to end. For this example, let's take the same values as our initial values, except let's just increase z to 0.1, but this time we'll do it permanently. And we'll then be able to observe how the economy moves from one steady state to another. Now, to do this, we want to make sure that we move to a new steady state, and we can use the steady command in exactly the same way we did before. This time it will find a steady state with z equal to 0.0 or to 0.1. That should be enough to observe it. Again, we've increased the number of periods so that we don't have end of simulation effects. Let's close this so we can see what happens in this case. Dynare, name of our model file. In this case, you see the same output, except we have two different steady states here, and it's not surprising that they're slightly different. Let's look at how our variables respond. Again, we'll look at capital. First, let's look at what happens in the z-shock. We move simply from this the initial steady state in period 1 to a new steady state in period 2. I'll show you a trick here in a minute to see if you wanted to move that transition later a few periods forward. Let's look at what happens to capital. Over time, again, as you'd expect, we'll move to a new steady state, and I won't show you that tail behavior, but you can see that capital slowly adjusts up to this new steady state. If I showed you the full plot, you'd see that it's just asymptotically becomes very close. Alright, now let me show you how you would push that transition forward from happening in the first period to rather happening later on. We do that by adding the shocks block back in, and here we'll do exactly what we did before. Specify the variable, specify the periods, and let's say we want to move it forward to period 10. Then we'll say for the first 9 periods, set that shock back to 0, and then end that block. We can save that and run that once again. Here we can look at what happens to capital in that case, and you see that once again agents are anticipating the regime change to a productivity shock, or to an increase in productivity, so they decrease as they anticipate. They decrease the capital stock and then increase up to that steady state. The applications of these techniques are varied, and your specific problem will dictate how you want to do this. Alright, let's move on to stochastic models. Before we do that, let's clear out what we've got here, just to give ourselves a clean workspace. If we move back to our model file and move to our stochastic model, you'll notice that we'll follow the same pattern as we did with the deterministic case. We'll specify a shocks section, block of our model file, and in this case we'll specify our variable epsilon, which is our only exogenous variable, as being the variable that we're shocking. There are two different notations you can use here. The first is to specify standard error, the standard error of your model, or of your shock process rather. we can do that by just typing the standard deviation for the epsilon process. Remember, it's normally distributed mean 0. In this case, we could do so like this. And of course, we want to end like that. There's another way to do this, and that is to initialize a parameter up here called sigma, and set it equal to 0.02. We'd add it to the list of our parameters. And I guess to be consistent, I'll call it C sigma and change that there. Then down here, we could say C sigma. One final way to do this is with a different notation, and that is to set this equal to C sigma squared. Note that in this case, we're specifying the variance, not the standard error in this case, and we would eliminate this line. Alright, now we're ready for computation with a stochastic model. In this case, we won't use the simul command, we'll use the stochastic simulation command. Now, this command, as you'll see, is far more flexible because there's a lot more that Dynare will give us out of this. There are several options that we can specify along with this command, and we specify those in the parentheses. I won't go through all of the options that you can use in this, but we will cover just a couple of them. The first one is order. Remember that the order, remember that the solution method that Dynare is using for a stochastic model is a Taylor series approximation about the steady state of our model. These follow, there's a literature that calls this perturbation methods that explains the theory behind this more clearly than we'll go into here. The order specifies the order of our Taylor series approximation. Dynare will handle orders 1, which would be a linear approximation, 2, and 3. There is a C++ standalone package, Dynare++, that we won't talk about today, other than to say that Dynare++ will handle k-order approximations as high as you need it to be. Dynare, at least the version 4 that we're using with MATLAB today, will handle orders 1, 2, and 3. So we can specify a quadratic ordering or quadratic approximation of our model in this case. Another thing that we might want to do is tell Dynare how far out we want our impulse response functions to go. This is done with the IRF option, and we just specify some integer, and in this case let's choose 40, which actually is the default that MATLAB uses, or that Dynare uses, but we could set it as long or as short as we wanted to. There are many other options that you can do with stochastic simulation, the stochastic simulation command, and we won't go into those right now, but note that the documentation for Dynare is very good with in explaining what those options might be. So we'll save that, and just as before, we'll come back over here and invoke Dynare by typing Dynare and then example stochastic. And again, remember that you need to have your current folder set to be this the same folder that contains your model file. Okay, let's run this and see what we have coming out. You'll note right away that the output for the stochastic case is much more verbose than the output for the deterministic case. And as we go through, you'll understand why that might be. Let's first go through what is printed by MATLAB. We have the same things going on that we had with a deterministic case, up through and including the steady state results. It finds us our steady state, and then it will go into things that the deterministic output didn't have. First, it will give us a model summary. It will tell us the number of variables, which was 8. The number of stochastic shocks is 1. The number of state variables is 2. In our case, that would be capital and our Z, or our productivity variable. The number of jumpers is maybe somewhat confusing. MATLAB or Dynare makes a distinction between what it calls jumper variables and what it calls static variables. Now these are going to be variables that are not state variables and not exogenous. So endogenous non-state variables. The distinction between jumpers and static are that jumpers for Dynare are the variables that are forward-looking. In our case, these would be consumption and the interest rate. Both had t+1 variables in them. In the case of all the other 4 variables, they were only current period variables. So that would be investment, output, the wage, and labor. Okay, moving on, it gives us our variance covariance matrix of our exogenous shocks. In our case, where this is fairly uninteresting since we only have one shock, and so the variance is just the variance covariance matrix is just the variance that we specified. It gives us our policy functions. The way that this is set up is that it gives us the variable as a function of a constant. It makes a correction that we won't talk about here, and then gives us what the period today's output, for instance, will depend on capital yesterday, productivity yesterday. These are our 2 state variables, our exogenous process, and then the quadratic terms of those. And you can see that we have the same for investment, capital, labor, the interest rate, the wage rate, consumption, and Z. The next thing that Dynare prints in its output are the theoretical moments, which is incredibly convenient that it will do this for us so quickly without us needing to write complicated programs with lots of simulations. And note that the total time this took was 8 seconds. Then it gives us correlations between all of our variables and autocorrelation up to the 5th order autocorrelation for each variable. Remember, it also gave us these graphs. I'm going to expand this so we can look at these more closely. The red line is the 0 line, naturally, and it gives us 40 periods of response to a 1 standard deviation impulse in our shock epsilon. If we had more than one shock, it would open more than one figure with these plots. I'll show you in a moment that it also will have the data that generate these plots will also be saved where we can use it. In fact, let's do that now. Once again, all of our almost all the relevant details of the output that you'll be interested in will be in this OO global variable. Let's open it and we can look at some of those things. The steady state, once again, is saved here. It saves our means, and these are again in the order that we specified the endogenous variables. So this is the steady state for output, investment, and so on. It saves the variance, and this is actually the correlation matrix between each of our variables. Oh, I'm sorry, that's incorrect. These are the variances and covariances between each of our variables. And then similarly we have our autocorrelations. Here's the impulse response functions I was discussing earlier, and you'll see that it's a structure itself, and the notation here is that you have the variable underscore the shock. So if you have more than one shock, it would follow right here. It would follow right afterwards. You'd have a list of several of the impulse responses for the next shock. Let's take a look here. I opened up what Z looks like, and we can take a look, and it's the same plot that we were seeing earlier for Z. Alright, let's take one last look at the model file, and we can review just briefly what we've done so far. So far we've talked about how to specify a model file. The 5 blocks are the preamble, the model block, the initial values and steady state, the shocks block, and the computation section. We've covered cases for deterministic models and for stochastic models. Note that we haven't done anything with data or estimation yet. In our next segment, we'll talk about the Bayesian techniques that Dynare employs to estimate model parameters.